And now it's my great pleasure to introduce the first talk here to the conference. It's the German region's keynote speaker, and we have invited Ruth Keogh. I'm not sure if I really have to say a lot about Ruth because she's very present in our community and she's very well known. She is a professor of biostatistics and epidemiology in the medical statistics department at London School of Hygiene and Tropical Medicine. Her research focuses on statistical methods for the analysis of observational data, and she works especially on causal inference methodology and methods for the analysis of time-to-event data. She's particularly interested in addressing practical challenges arising in real applications and is involved in a number of areas of application in health research with a particular focus to cystic fibrosis. She also works on other areas of crucial importance, such as methods for handling measurement error and missing data, prediction modeling, and design and analysis of case control studies. Dear Ruth, we are very grateful that you have accepted our invitation, and we are looking forward to your lecture with the title, Causal Inference with Observational Data, a Survival Guide.
Thank you. Can I take this? Thank you. Thank you very much, Annette, for that very kind introduction. It's great to be here. I'm very grateful to Annette for the opportunity and to Frank and the other organisers, especially to be here in this very nice city and venue. Right, so let's get started. I was thinking a lot about what to talk about, and I wanted to give quite a general talk in a way because I know that it's a wide audience of people with lots of different expertise here and experiences. So anyway, I hope I made a good choice on deciding to talk about this topic of causal inference with observational data, a survival guide. What's this talk going to be about? It's going to be about asking and hopefully answering what-if questions. So questions about the effects of treatments when the outcome is a time-to-event outcome, so like a survival time, for example. So it's about answering questions like, what if people took treatment A versus treatment B, for example? And in particular, I want to focus on how we can try to address these questions using longitudinal observational data rather than, say, data from a randomized trial. So in a little bit more detail, these are the aims that I was hoping to cover. So I wanted really to give a bit of an overview of different methods for estimating effects of treatments on survival, and especially, hopefully, to provide a bit of practical insight into how some of these methods work. I also wanted to, I think when I first started working in this area, some of these causal inference methods were quite mysterious to me. They seemed quite disconnected from the things that I was taught as part of my training. So I also wanted to try and make some links between these methods and what we might think of as more traditional methods that we're perhaps all more familiar with. And this is work, or a part of larger work with John Michael Gran from the University of Oslo. I felt I should give a bit of a disclaimer at the start of this talk in that although I've been working in this area, for quite some time now, I'm sure I'm not the greatest expert in this field in this room. But I thought, as part of the opportunity to give this talk, I wanted to set myself the challenge of giving an overview of some of these different methods. So I hope you'll find it useful. So what are the ingredients that we need to have to do a kind of study which is about estimating causal effects of treatments or other exposures on survival? Well, of course, everything we do, it seems very obvious, but it's not always the case. We need to start with a question, some research question. And I think this is sometimes a bit more difficult than it sounds. It seems so obvious that we need to know what we're aiming to do, but maybe sometimes it's quite difficult to have those discussions with our clinical collaborators and really ascertain what the question is. Because of the topic that I'm focusing on today, we're thinking of questions in which we really need to have a clear specification of what the treatment strategy or strategies are that we're interested in and what the outcomes are, which I'll say a bit more about in a minute. Having specified the question in detail and having thought about what treatments we're interested in, what outcome we're interested in, we're then in a position to give a clear statement of what our estimand is, or what our causal estimand is. So this is a description of how we're going to measure the effect of these treatment strategies on the outcome. So the focus is on time-to-event outcomes, and as soon as we're thinking about time-to-event outcomes, we're sort of inherently in a longitudinal situation. And so there's all kinds of different options about the type of treatment strategy that we might be wanting to investigate. So we might be interested in treatments given at a single time point as a one-off. We might be interested in treatments that are sustained over time, such as many treatments used in chronic disease. We might be interested in dynamic treatments, which are things like treatment strategies like initiate this treatment when your blood pressure goes above some level, or treatments that are given within some grace period so that the person doesn't get them immediately, which might, for example, be the case in cancer treatment, where one's treatment doesn't start immediately. And everything always seems to get more complicated when we move to time-to-event outcomes. So there's not just one possibility. There are lots of different possibilities that we might be interested in terms of the nature of our outcome. So we might be interested in overall survival or all-cause mortality. We might have competing events. We might have recurrent events. And we're going to need to specify the time horizon over which we're going to observe these events. It might be short, or it might be years. Once we've specified those things, we're then, as I say, in a position to say something about what the estimand is. And this is a statement about what the type of effect is that we're trying to estimate. So how we're going to measure how this treatment strategy of interest is related to this outcome of interest. And we might be interested in estimating the treatment effects at a population level or marginal population average or marginal level. We might be interested in conditional average treatment effects in a subset of our population, or we might even be interested in the effects of the treatment among those who actually received it. There's also more to the type of effect, not only whether it's marginal, conditional, or whatever, but how we're going to measure it. And again, in the time-to-event setting, there are various options here. We might be, we're all very familiar with hazard ratios, of course, and I certainly find the hazard ratios, still extremely useful summary measure of association between exposures and outcomes. There has been some criticism in recent years of the use of hazard ratios as a way of measuring causal effects. And so what I'm more going to focus on today is estimating risks, so absolute risks in treatment groups or survival probabilities. And then we can think about quantifying causal effects in terms of differences between risks or ratios, for example. So this is the setup. Once we've specified all those things, we're then at this stage of deciding, we've got our question, we've got the thing we want to estimate, and presumably along the way we've got some data in mind that we're going to use for this purpose. And so the last stage is, what tools are we going to use to actually estimate this thing we've specified here? And this last stage is actually the stage that I'm going to focus on, but assuming that we have all these earlier things very clearly set out. There's lots of tools that have been developed over recent years and decades in causal inference, including things like marginal structural models, inverse probability weighting, G computation, G estimation, and more recently, doubly robust methods. And as I mentioned earlier, some of these, particularly when I started trying to get into this area, seemed quite mysterious to me, and some of them still do, I should say. And I wanted, as I also mentioned earlier, these things, these causal inference methods, they do make use, which I find reassuring, of things that we're all very well familiar with in the time-to-event analysis context, like non-parametric methods like Kaplan-Meier analysis, Cox regression, or other semi-parametric or parametric models, discrete time analysis, etc., etc. I'm not going to give a whole lot of references during this talk, but I just wanted to point out in a few places some references that I found particularly useful from a practical point of view of learning about some of these approaches. So in terms of causal inference methods, there's a huge literature on this now, but this book from Hernan and Robbins on what if is, I found, particularly useful and gives a really nice overview of this topic, including for time-to-event outcomes. And there's an even bigger literature, of course, on more traditional statistical methods in this area. But as a starting point, I like this paper from the Stratos Initiative from Anderson and colleagues on this tutorial in biostatistics. So we have this sort of process that we set out, starting with the question and ending up with how we're actually going to answer that question in a practical way using the data. Now, this is really a slightly shortened version of other processes that have been described in the literature. So I'm sure many people are familiar with the target trial emulation idea. I think there was a short course on this topic yesterday, so many of you will be experts on this now, described by Hernan and Robbins, in which they said if we have a causal question about effects of a treatment or exposure on an outcome that we're going to address using observational data, then a good place to start is to explicitly describe a target trial, so the trial we would like to do if it were feasible, and then to describe how we might go about emulating that trial using the data that is available to us, sort of filling in all of these headings in a protocol. It's also very closely related to this causal roadmap, which was described, I think, maybe first of all in this 2014 paper, so quite some time ago now, from Peterson and van der Laan. But I discovered recently this very nice sort of update paper on this, a causal roadmap for generating high-quality real-world evidence, has appeared this year on the archive. And they take us through in this causal roadmap, a very detailed process, starting with the causal question and estimand, and ending up with some, not only an analysis, but sensitivity analysis and comparison of designs and methods. So I think these are really useful sort of frameworks for structuring these types of questions. So, as I said, I'm going to focus primarily on the tools, but I will mention some of the other aspects. And I wanted to put this in some kind of realistic context. So I'm going to focus on a case study, which is in the area of type 2 diabetes. And this is work with Daniela Weir from Utrecht and Nan van Geloven from Leiden. So we're in the setting of people with type 2 diabetes and adults. And we're imagining a study with people with this condition who have been taking metformin, which is the first-line drug treatment for people with type 2 diabetes. So I've just got an example of 10 individuals meeting these criteria here. And these are also people who've reached a certain stage in their disease, their type 2 diabetes, in which their HbA1c, which is a biomarker, has gone above some level, and their doctors are thinking about giving them some second-line treatment in addition to metformin. And there's a number of second-line treatments that are available. Just for the purposes of this talk, I'm going to focus on one particular of those treatments, which is SGLT2. So we have some observed data, people who haven't yet had any add-on treatment. And then in our observed data, some people remain observed and they still don't have any add-on treatment, but some people have an add-on of this second treatment, SGLT2. We also have our outcome. I'm going to focus on all-cause mortality for this talk. But alongside, we've got our eligibility criteria, treatments, and outcome. We also have a lot of other information on these individuals in this data. So we have some sort of time-fixed covariates like age and sex and smoking. And we also have a lot of longitudinal information that's going to be needed. So how long these people have had type 2 diabetes, their HbA1c, their BMI, so some continuous variables, and also information about whether they have a number of comorbidities. And I should say, this is not actually real data. It's inspired by a real data question. I think that actually quite a lot of groups are working on this real question. But we developed this synthetic data as part of a different project, actually, in which we wanted to have a synthetic data resource in which we could try out some different causal inference methods and compare the methods, but without the difficulty of getting lots of people access to some large-scale health data. So what is this data set? We designed it to mimic longitudinal electronic health records data, and we wanted it to be something that enables us to try out answering different types of causal question, but we wanted also to design it in such a way that it doesn't particularly favour one analysis method over another, so we're not setting ourselves up to do really well using one particular method. And also, we want to make it openly accessible, not yet, but that will happen soon. And we were also inspired by this paper from Sarah Friedrich and Tim Fried on the role of benchmarking datasets and simulations in method comparison studies. And there is a session on this topic later in the conference, I think later this morning. So that's a bit of an aside. Now back to this topic. So I'm going to focus on two different types of question that we might want to answer using this data, which are representative of the types of questions we might want to answer in wider settings in health. So we're going to think of, first of all, answering a question about a treatment strategies that just refers to giving treatment at a single time point. And then to the more complicated situation where our treatment strategies are going to involve sustaining some treatment over time. So for the point treatment strategy, our research question is, what's the impact on all-cause mortality of initiating this second-line treatment, SGLT2, now versus not adding any treatment now? So our treatment strategies are here: add SGLT2 now, do not add any second-line treatment now. And when I say now, I'm thinking of these patients, these individuals here, who have reached some point. They haven't yet added any second-line treatment, but their doctor is thinking about it. So, I say now, and that means that we're just making a statement about a treatment given at this moment. We're not making any statement in these treatment strategies about what might happen tomorrow or next year. Under the sustained treatment strategies question, we're just extending this slightly. So our question now is, what's the impact of all-cause mortality, not just of starting the treatment, but of starting and continuing a treatment, this second-line treatment, SGLT2, versus not using any add-on treatment, but not using any add-on treatment for the period of follow-up of interest. So here's our treatment strategy: start and continue SGLT2, or do not add any second-line treatment for up to 3 years. And that 3 years is our time horizon of interest. And for both of these questions, we're focusing on the same type of estimand, the average, or in other words, marginal survival probabilities up to 3 years, and the differences in those things between the two treatment strategies. So I'm going to talk through these in turn, starting with the point treatment strategies and then moving on to the sustained treatment strategies. So here's a reminder of the data that we're going to use to answer this question about whether or not it's a good idea to, on a population average level, to add this second-line treatment or not. So we're also going to depict the data in another way, using a DAG, which is going to be useful for thinking about how we're going to use the methods that I will try to provide an overview of. So here we're depicting the data using this causal diagram. So we have treatment observed over time, and we've got 3-year follow-up here, so we've got 3 time points. So A is denoting treatment, it's binary, no add-on, or adding this second-line treatment here. We've got some baseline variables x, which don't change over time, and then we've got these variables L. So L here are time-dependent variables, and L is representing a collection of variables here. And we have our time-to-event outcome, which is all-cause mortality. So this is an indicator of having the event at each time. Now, I've drawn the DAG here in discrete time, just for the purposes of making the picture, but I'm also thinking of observing the time to event in continuous time, in which case we could imagine this DAG being drawn with very short time intervals here. So for this question about a point treatment strategy, we're thinking about what would happen if we were to intervene on this baseline treatment status here? Because it's just about treatment given at a single time point. So what would happen if we were to intervene on A0 and give everyone the second-line treatment, or if to intervene and stop everyone from getting the second-line treatment at that time point? But again, we're not saying anything about what happens later. And of course, if we intervene on this treatment at this time point, that's going to have knock-on effects on, well, potentially has knock-on effects on these subsequent outcomes, but also on these L variables. So in order to specify sort of more formally what it is we're trying to estimate, let me introduce this potential outcomes notation. So we're going to let yt with the superscript of A0 be our potential outcome at time t under this particular treatment strategy A0. So if we were to set capital A0 to little a0. And alongside that, we've just got the corresponding continuous time version of that. So t with the superscript is our potential event time, thinking of that as a continuous time thing. This allows us to specify what exactly it is we're trying to estimate. So as I mentioned, we're focusing on average survival probabilities up to 3 years. So we can write those in time in terms of these discrete time outcomes. So here we've got the average survival probability at time t under the intervention of giving the second-line treatment at baseline, or under the intervention of not giving any add-on treatment at baseline. And this at the bottom here is just the risk difference, corresponding risk difference, or we could just equivalently describe that in terms of the discrete time, the continuous time outcomes written in terms of t here, and probabilities of that being greater than some value little t. So this is what we're aiming for. And so these are average survival probabilities. And sometimes I think it's not always clear when we say average or marginal probability what exactly it is we're averaging over. And I think it's important to really be clear about this in this situation. So going back to this diagram here, we're thinking of this population here, which is drawn from people who are meeting these particular eligibility criteria. They're on this metformin, they've got their HbA1c above this level, they're adults. And they've got some distribution of all these other variables at baseline. So they've got a certain age, sex, smoking distribution, and a certain distribution of all these longitudinal covariates at baseline. So that's the population of interest. So that's the population that we're averaging over when we're thinking of these average or marginal survival probabilities here. And so if we were in a slightly different population with a slightly different distribution of those characteristics at baseline, these averages would be referring to a slightly different population. So that's what we're aiming for. And I'm going to talk through 3 particular methods now for estimating these estimands using this data that we have. So I'm going to use some inverse probability of treatment weighting, the G formula, which in fact is simple standardization in this context, and then a doubly robust extension of those things. But I'm also happy to say that these methods, involve, again, things that are familiar to us, as you'll see. They involve using Kaplan-Meier methods, logistic regression, Cox regression, or whatever your favorite regression model is in time to event analysis. So let me start with inverse probability of treatment weighting. So here's our data again. I'm just going to put the DAG at the top there to remind us what the setting is that we're in and that we're intervening on this variable. This is the thing we're aiming to estimate with all of this. Now, in this DAG, we can see the association between A0 and later outcome is confounded by these variables here, by x and L0 in this case. We don't have any, in this setting of a point treatment, because we're only thinking of intervening at this first time point here, we don't have any more complex confounding like we'll come across when we think about sustained treatments. So we only need to worry about, as I've drawn it here, about x and L0 in terms of confounders. So this is what we're aiming to estimate, the probability that under some intervention at time 0, the event time would exceed time little t. Now, of course, due to this confounding, that is not equal to just the observed probability that t exceeds little t in the people who were observed to have been given the add-on treatment at baseline. But we can use a simple approach to deal with this confounding here. One way of dealing with it is that we can write this probability, which is in terms of the potential event time here under that intervention, as this observed probability, but in a weighted population. So in a weighted population in which each person who had this treatment, who had the add-on, was actually in real life given the add-on treatment at baseline, receives a weight. And that weight is going to correct for the fact that these x and L0 variables are confounding the association between A and Y here. So the weight that each individual are going to get is the probability that they received the add-on, 1 over the probability they received the add-on treatment given their characteristics at baseline. So, very simple step, we need to estimate this probability and find this weight. Having done that, we can then obtain survival probabilities under this treatment strategy, or under both treatment strategies. We can do this for A equals 0 as well, using simply a weighted Kaplan-Meier approach, so inverse probability of treatment weighted Kaplan-Meier analysis. So, the only difficulty here is estimating these weights. So in order for this approach to work, it relies on getting the model for these weights right. And I'll come back to this in a little bit. Let me move on to this second approach, which is the G formula or standardization. And I have to say that I don't know why, but for some reason, weighting doesn't come that naturally to me. Maybe it was the way that I was taught when I was learning, but regression adjustment somehow comes much more naturally to me than weighting, and that's why I find this G formula approach particularly nice. So here's what we're aiming to estimate again, this probability, which is written in terms of our counterfactual event time. And just using straightforward standardization, and under these assumptions, that I might have forgotten to mention, but are extremely important. Let me go back. I've mentioned the assumption that x and L0 are the only confounders here, as we've drawn it in the DAG. We're also making these additional assumptions, let me not forget those, of positivity, that everyone has a non-zero chance of getting each treatment strategy. And also this sort of funny consistency assumption, which means that the counterfactual event time under the, if a person were to be assigned the treatment strategy that they were actually observed under, would be equal to their actual observed outcome. So under these assumptions, again, we can use simple standardization and write this probability of interest like this. So now it's just written in terms of things we observe, not counterfactual outcomes that we don't observe. So we've got this conditional probability of t being greater than t observed t, given A, given X, and given L, and we're standardizing over the distribution of X and L0 at baseline here. Now, if X and L0 were both binary or if they're categorical, then we could estimate this thing quite easily. I've written it assuming they were categorical using sums here. We could estimate this thing quite easily in a non-parametric way, but in the diabetes example, X and L are actually collections of variables, and that's representative of a general setting. Usually we have quite a lot of variables that we want to adjust for, in which case we're not going to be able to just plug in the values here. And so we can use instead an empirical standardization approach in which we're simply going to estimate this probability of t being greater than little t, plugging in A0 equal to 1, which is our intervention of interest, for each individual, no matter what treatment they actually received, so setting their treatment to 1 at baseline, but using their observed values of x and L0. And we're simply going to estimate that conditional probability for each person and take the average over everyone. And so what we need to do here is specify or is have some model that enables us to estimate these conditional probabilities here. And so we can do that using some model, for example, a Cox model, but whatever model you like. So here we've got a hazard model in time t, conditional on treatment x and L0. I've just written it in terms of a simple model here, but we might have more complexity in this model. Having fitted this model to our observed data, we can set x and L0 for each person to their observed values, and we can fix A0 at the value of interest, and then take this average. So this is a very simple and nice approach, to me anyway. So we have these two approaches, inverse probability weighting, and then this G-formula approach. The third approach is, I'm not going to give a lot of detail about, but the inverse probability weighting approach, we had to specify this weights model. And in the G-formula or standardization approach, we've had to specify some model that enables us to get these conditional probabilities. We need to make some assumptions there, which we're quite likely to get wrong, those models. And so this doubly robust approach just gives us two chances to do well. So the doubly robust approach combines those two methods of inverse probability of treatment weighting and the G-formula. And it performs the G-formula just in a weighted way. So each individual is going to be weighted in this model that we fit to get these conditional probabilities by their inverse probability of treatment weight. And this is going to give us consistent estimates if either the weights model is right or the outcome model is right. And there's lots of doubly robust methods that have been described in the literature, and this is just one. And again, there's a huge literature on these methods too, papers that have come out in quite recent years that I found particularly nice and useful for describing these approaches are this paper from Robin Dens and colleagues and from Arthur Chaton and colleagues. And let me just show you some results. As I said, this is not real data, so in a way these results are not especially interesting, but we did set it up in order that things would go in the expected direction based on people who know about this topic. So we've got our two treatment strategies, point treatment strategies, and we're showing under our three methods there, weighting, G-formula, the doubly robust combination, these survival curves under those strategies, and the confidence intervals all obtained using bootstrapping. What we see is that, I think as we would expect, the weighting approach is giving us more variable estimates. That's what we expect. That's what can happen when we're using inverse probability of treatment weights. The G-formula is giving us slightly a smoother curve because that's based on averaging rather than a weighted Kaplan-Meier. And the doubly robust is giving us confidence intervals slightly in between. This is simulated data, so we know the truth, and that's given by these dotted lines, but don't focus too much on that, because these estimates are just from a single data set. And I'm not showing it in this talk, but if we repeat this simulation lots of times, then the truth, fortunately, gets closer to, or what we estimate gets closer to what the truth is. So that's just an example of what the results might look like from this, applying these types of approaches. So let me move on to this more complex setting of trying to estimate the effects of treatments that are sustained over time. So this is our second question here. And we're not just thinking about giving a treatment now, we're thinking about starting and continuing a particular treatment strategy, either this add-on treatment or no add-on treatment. So in the point treatment situation, we were just intervening here. In the sustained treatment situation, we're thinking about what would happen if we intervene not only at baseline, but also on these other treatment at these subsequent time points. So again, we need to introduce some notation here, and this is extensions of what we saw in the point treatment situation. So we're introducing potential outcomes. We've got A underline 0 here, and this is now representing the sustained treatment strategy starting at time 0 and going on. So we're going to specify A0, which is underline, which is the treatment at time 0, 1, and 2. And again, we've got the corresponding continuous time version of this event time. We've got our estimans again, which look very much like we had in the setting of the point treatment, the only difference being that instead of just having A0 here, we've now got this underline, which is representing the fact that this is something that's sustained over time. And again, these are average survival probabilities up to 3 years, and just a reminder that we need to think about what these are averaging over. So we're imagining taking these individuals who in reality followed a mixture of treatment patterns over time, and we're thinking what would happen if we started them all on this second-line treatment and they continued it over time, or what would have happened if we'd not given any of them up to 3 years this add-on treatment or any other. And we're now in a bit more of a horrible situation in terms of the confounding. So when we were just thinking about the point treatment, we only had to worry about confounding by these baseline variables x and L0. But now we've got this kind of funny situation where we've got this feedback between A and L over time. So if we think about estimating the sustained effect of this particular treatment strategy on the outcome at time 3 here, in a sense, we want to adjust for L2 because that's confounding the association between A2 and Y3. But in another sense, we don't want to adjust for L2 because it's on the pathway from the earlier treatments to the outcome. And so this is really the challenge of time-dependent confounding, that we have feedback between these L variables and A over time, and the L's also being connected to the outcome. And this is a really nice paper from Rhiann Daniel and colleagues on methods for dealing with time-dependent confounding. And I don't know whether Rhiann's here yet, but I think she's giving a talk on mediation analysis later in this conference. So this time-dependent confounding requires some special methods for dealing with this. And I'm going to talk us through briefly some of these different methods: inverse probability weighting, an extension of that, the cloning, censoring, and weighting approach, an extended version of the G formula, and a doubly robust approach. And again, you'll see that what feeds into these tools are all these things that we're very familiar with. So starting with the weighting method. And all of these things are just extensions of what we described for the point treatment setting. But we can't just do simple weighting at baseline in the setting of a sustained treatment. We have to start with a model here. So we're going to start with a marginal structural model. And a marginal structural model is a model, in this case a hazard model, for how the treatment relates to the counterfactual or potential outcome. And I've written that here as a hazard model for the continuous time outcome T under this treatment strategy A underline 0. So this, I've just used the Cox model here. We could use any hazard model here. We've got a baseline hazard, and then we've got what the impact is of treatment. And this is a very simple model. I'm just saying here that the hazard at time T only depends on current treatment, but we could allow it to depend more generally on the history of treatment up to that time. So we specified this marginal structural model. It doesn't have any other variables in it. It's only a specification of how this counterfactual outcome relates to treatment. So no L variables or X variables in there. Now, we can't fit this model directly because of all this horrible time-dependent confounding that's going on, but we can fit it using time-dependent weights. And so, again, we need to estimate these weights. And in this case, they're changing over time to account for the fact we've got a sustained treatment. So up to time 1, the weight for a given individual in our data is going to be the inverse of the person's probability of receiving the treatment they received, which is 1 or 0, given their baseline variables. At time 2, we're multiplying that by the probability of them receiving the treatment they received at time 1, given the past, and so on. So, sort of informally, this is 1 divided by the probability that a person received their observed treatment pattern over time, given their other characteristics. So we're multiplying probabilities up over time here, and what that can result in is something quite small in the bottom here, and this can result in the weights becoming quite large, which is an issue of this inverse probability weighting approach. One partial solution to that is to stabilize these weights, which we've just done by adding these probabilities on the top here, and there are some different ways of doing that. So once we've estimated these weights, which we can do using logistic regression, a series of logistic regressions, our final step is then to fit this marginal structural model, and that requires assumptions about how the treatment over time relates to this potential outcome. We fit it, but each person is weighted over time using time-dependent weights in this way. And we're then able to set we estimate the parameters of this model. We can then simply set A to 0 or 1 and obtain survival probabilities in the usual way after fitting a Cox model. A bit of an extension to that, or well, maybe not an extension, but a version of that is this cloning, censoring, and weighting approach, which is becoming quite or has become over recent years, I think, very popular in the applied literature. I think because it's quite a nice, intuitive approach. So let me just describe briefly how this method is working. So this is our original data, our observed data. We've got all this mixture of treatments and non-treatment going on. The first step in this approach is to just create 2 copies of the data. That's the cloning bit. And we're going to label 1 copy for each of our treatment strategies of interest. So we've got this copy labelled as our untreated or no add-on group, and this copy labelled as the SGLT2 add-on treatment group. So I haven't done anything to the data yet. But the next step is the censoring step is to now manipulate this data in such a way that it looks like everyone has followed this treatment strategy. And this seems like cheating, but we're going to deal with the fact we've done that in a minute. So we simply censor people when they deviate from this treatment strategy. So in this top picture, we're censoring people when they deviate from being untreated. And some people are treated immediately, so they sort of disappear immediately from the data. And at the bottom, we're censoring people when they deviate from being treated, which again, for some people, is immediately. So we're left with these partial data sets that we've created through this censoring manipulation. And of course, we can't just proceed without doing anything about the fact that we've manipulated the data in this way. And so we're going to deal with the fact that we've essentially induced dependent censoring in our data by doing this. And so this artificial censoring can be addressed using inverse probability of censoring weights, which is something we might do, in a standard survival context if we thought we had dependent censoring. So our inverse probability of censoring weight at a particular time it's in fact for people who remain in the data is the same as their inverse probability of treatment weight that we had in the previous approach. Having estimated these weights, we can then fit a Kaplan-Meier to the untreated using these weights, and a Kaplan-Meier to the treated data, manipulated data given these weights, and obtain these survival curves of interest. We could also do various other things, having created these data sets. We could combine these and fit a weighted marginal structural model instead. And this approach has seen a lot of use in the literature, is described for example, in this 2008 paper from Miguel Hernan and colleagues, and we also did some work published earlier this year to link this approach to the marginal structural modelling approach. So, getting towards the end of these methods, the next approach I want to mention is this G-formula approach. And I really have to apologise for the equations in these next slides, because you might be all better than me, but I'm absolutely terrible at following equations in talks. So I've let myself down a little bit here. So in the point treatment setting, the G formula was standardization. And so we had this formula. This is just a reminder of what we had before. We had our probability of interest. I've written it in terms of risks here instead of survival, because that's just a little bit more convenient here. It's written as this conditional probability, standardized over the distribution of these baseline variables. Now, in the sustained treatment setting, we can extend this standardization idea. So I'm just going to try and explain this briefly. I don't know how well I'll explain this, but for estimating the probability of risk up to time 2 here. So in order to have the event up to time 2, you either have to have the event at time 1, or you have to survive time 1 and then have the event at time 2. So that's what I've written here in terms of the potential outcomes. This first piece, which is just the probability of having the event at time 1 under this intervention, it's basically what we had before. We can do standardization. For the purposes of fitting these things on the slide, I've just omitted X for now. We can imagine that absorbed in the L0. So that's easy. This second part, which is the probability of surviving to time 1 and then having the event at time 2, is given by this a bit more complicated formula. But I'm sure if we, maybe you're all better than me at writing this, at seeing how these things work on a slide. But I think we could all write that out if we were to sit down and think about it. So we've now got these various models involved, models for, or probabilities written in terms of the outcome Y given the past, and the outcome L given the past. This is that same formula just repeated at the top there. And just what I want to emphasize here about how this method works is that we're now in a situation where we need to specify all these models under this approach. And in particular, we need to specify these models for L given the past. Now, this might be okay if we just had a single L variable and a small number of time points to consider. But in the diabetes example, which, as I mentioned, is representative of a lot of situations that we face, L is actually a collection of, I think, 8 different variables. And so we're going to need to specify not just one model for the L's here at a given time point, but a model for each of these L's, which are not conditional on the others, which requires us to make some assumptions about how these things are ordered in relation to each other over time. So as soon as we have a lot of L variables, this G-formula, a parametric G-formula approach, requires us to specify quite a lot of different models, all of which we're at risk of getting wrong. So in terms of the practical steps of this method, if we're willing to specify all these models, we would fit them all. We'd choose a model for Y2 given the past, Y1 given the past, L1 given the past, and so on. Fit those models, estimate the parameters of those models. We then take, for each individual, their observed baseline variables, X and L0. That's our starting point for each person. And then we would use these models and set A, treatment, to the value that we're interested in, so SGLT2 or no add-on over time. And we simply simulate through this DAG using these models and setting A to a particular value. And this gives us an outcome for each person, which we would then average over individuals. So it ends up being a simulation approach. And this has been described, surprisingly perhaps, as the NICE approach, which stands for non-iterative conditional expectation G-formula approach. There is another G-formula method, which I think is less well known, but which I've been learning a bit more about recently, which is called the ICE approach, which stands for iterative conditional expectation. And to me, this is an even more horrible formula that I can't really read, but I'm very happy to share these slides, and there's some references given in a minute. But it's another way, it's an equivalent way of writing this probability. And again, I'm just looking at 2 time points, and there are, of course, general versions of these formula which extend to a general setting of many time points. The nice thing, I think, about this alternative, but perhaps less well-known G-formula approach, this ICE approach, is that it means we don't have to specify all those L models, which when we have a lot of L variables is going to be a challenge or require some, perhaps heroic assumptions about what some of those models are. It avoids having to specify all those models. We have to specify a lot of other models, but perhaps things that we're a bit happier to specify. So let me just go through the practical steps just to show you that, in fact, even though we have quite, to me anyway, a complex formula here, the actual practical steps to implementing this just require a series of regressions. So this first term here, which is a sort of double expectation, involves regressing the outcome at time 1 on the past, getting fitted values from that, and taking the average of those fitted values. That gives us this expectation here. The second, bigger expectation just requires doing that with another layer. So we regress the outcome at time 2 on the past, so past treatment, past L variables, and we get the fitted values from that setting treatment to the value that we're interested in, so 1 or 0. That gives us these fitted values, which are probabilities. We then regress those on the treatment and variables at time 0. So we're sort of starting at the end and we're going back in time using these regressions. We get the fitted values from that, and then we multiply these things together and we take the average. And to do this at multiple time points, we're just going to be sort of starting at the end and using this iterative procedure, going backwards and doing a series of regressions. And they're always regressions of the outcome on the past or fitted values of the outcome on the past, rather than involving models for these L variables. So I just wanted to give a little flavor of how that method, ICE method, works. And another reason I wanted to mention this ICE G-formula approach is that it's really the basis for a lot of extensions to doubly robust methods, one of which, for example, combines this ICE G-formula approach with time-dependent inverse probability of treatment weighting. So it combines the weight we would estimate under the first approach that we considered earlier with this G-formula approach. And it's also sort of the starting point for more complex methods like the TMLE, targeted maximum likelihood estimation. And here's 2 very nice papers that I found really useful, come out in recent years, for getting to grips with these approaches from Lan Wen and colleagues. And finally, let me just show you some of the results from applying these approaches. It's sort of reassuring that we see similar results across these approaches. So we've got our 2 sustained treatment strategies. We've got our results from inverse probability of treatment weighting and the cloning, censoring, and weighting approach here. And we're seeing, I think, as we would expect, quite wide confidence intervals here because they require the use of these weights, which can get large for some individuals. We get to be a bit more efficient by using these G-formula approaches, the NICE approach, the ICE approach, which this has a stepwise nature, not because we're doing something like Kaplan-Meier, but because we're doing we're fitting a series of expectations, and I've done that on a small grid of time, which gives all these little steps. And this is the extension to the doubly robust approach here. So, I hope I've managed to give a bit of an overview of these different methods for estimating effects of treatment on survival, both for the point treatment setting and extended into that sustained treatment setting, which is a bit more tricky to deal with. I've only covered, we had this slide near the beginning, I've only covered, a tiny subset of these things. I think it would be a lecture course to cover all of these things. But the methods that I've described can be extended to more complicated situations like dynamic treatment strategies, competing events, conditional average instead of population average effects, and so on. So I think the methods that I've described are really a starting point for answering more complicated types of question. And just to finish off, I think there's all these huge developments in the causal inference literature in recent times, but it seems that practical implementations of these methods are lagging behind those developments. Maybe, I guess that's the way with everything. I think it would be nice to see more comparisons of these different methods, both in specific applications and perhaps in simulation studies, which might be something that gets discussed in the session later on. Some of these methods can be computationally impractical in big samples. The data, I never really said how big my simulated data were, but it had 10,000 people in it. And the G-formula methods are quite time-consuming to apply, particularly if we're going to bootstrap the whole thing, which we did to obtain the confidence bounds on those survival curves. So some methods might be more practical than others if we have very large data sets. And I think extensions are also still needed to some of these methods, which have been done to some extent, but to handle the challenges we face in real-life data, like missing data, and especially of the fact that we've assumed throughout all of this, which is often the assumption with these methods, that the covariates on individuals are measured on this lovely regular grid over time, which of course is not the case in real data of this type. So I'll finish there. Let me acknowledge John Michael Gran, Daniela Weir, Nan van Geloven, and my funding from UKRI. And thank you very much for listening.